This is Algebra 2. We're looking at section 11.1. Okay, in 11.1 we talk about permutations and combinations. Okay, so in permutations, combinations, basically we're going to start talking about total outcomes. Okay, so we're going to look at total outcomes and basically how many things can we have coming about out of different scenarios. So one of the first rules we start looking at is the fundamental counting principle. Okay, and the fundamental counting principle, oops, spell principle wrong. There we go, principle, not principle. If we have separate events, so basically we have event M and event N, and they each have a total number of outcomes. What we do here then is we take and we multiply the separate events together to equal the total outcomes. Okay? Now, basically what happens here is we're talking about two things that happen. Not necessarily, they could be the same thing, but happening twice. So one of these things we could look at is how many possible arrangements are there if we flip a coin and roll a number cube. So flip coin and roll number cube. Okay, so on a coin there are two outcomes, and then we would multiply by a number cube which has 6 outcomes to have 12 different outcomes. Okay, now we're not talking about ordering within these outcomes or anything within. We're talking about how many total outcomes are there within this basic two events. Now we could flip a coin and flip a coin. So I could go coin and go coin 1, coin 2. There are two outcomes on a coin, a head or a tail, times a head or a tail. So we see that we have 4 total outcomes. Now if we think about a coin, we could also represent this as a tree diagram. We could say that on this coin we have a head or a tail, and then after we flip it we could have a head or a tail, or if we got a tail we could have a head or a tail here. So then we see that we could have a possible head, 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 tail, tail, head, tail, tail. Okay, so we see that there are 4 different outcomes happening here. But once again, even though this is one head, one tail, within here, the counting principle does not look at the order at which things are, whether the order matters or the order doesn't matter. That's where we start talking about permutations and combinations. So if we take a look at a permutation, okay, in a permutation, order matters. 2 T's in matters. So order matters. Okay. So this is very important when we're organizing things, and we have to have particular orders, or they're going to have different arrangements. For instance, writing a number. If I gave somebody a 96%, that's going to be different than if I gave somebody a 69%. Even though the numbers 9 and 6 are in both of those, they're different completely, so the order is going to matter on which things happen. So we look at the basic formula for a permutation. Okay, so permutation talks about NPR, where we talk about n factorial divided by n minus r factorial. So remember, the exclamation point is factorial. This is not saying n, it's saying n factorial. Okay, so we're not just putting emphasis on it, we are meaning it. Now, what is a factorial? For instance, 5 factorial talks about taking that whole number and multiplying by every, I guess, natural number below it. We don't want whole numbers because whole numbers have the 0. So we take 5 times 4 times 3 times 2 times 1, and we'd see that this would be 120 then. So this is our basic function for a permutation. Once again, order matters. Combination. Order does not matter. Okay, so for instance, if you were being selected to the varsity team in basketball, it doesn't matter if you're the first person selected or the 15th person selected, you're still on that varsity team. So if we're just looking at making the varsity team, that's when we start talking about that the order doesn't matter. Now, for positions and playing rights and everything, that's going to be a permutation, because that order will matter. Kind of like a first place, second place, third place ribbons would be a permutation. But if this order isn't mattering, that's when we talk about a combination. So we have to realize that a combination actually has less outcomes than a permutation. Okay, because what we do in a combination is not only do we do the permutation part of it, we also divide by an additional r factorial on here to take out any repetition of events. For instance, when I talked about 69% or 96% here, they're different letter grades. But if we talked about just receiving a 6 or a 9 in here, one of each, well, now both of those have a 6 or a 9, so that's where that order doesn't matter. So you have to be very particular on how you start working with these problems and looking at them, because there could be much confusion within them. There also are times that permutation, so it's going to go like this, this permutation could use the fundamental counting principle. I'm just going to abbreviate like that. So that fundamental counting principle sometimes can be used in that permutation. Sometimes we can use that permutation. You'll see how it kind of goes back and forth. So let's look at number 10. Okay, so number 10 tells us that to create an entry code for a push button door lock, you need to first choose a letter and then 3 single-digit numbers. How many different entry codes can you create? Okay, so we got a couple things happening here. We have a letter selection, so we have 1 letter and then 3 numbers. Now, one of the things within here is it did not say we cannot repeat our numbers. So repetition is allowed. Okay, if repetition is allowed, you have to use the fundamental counting principle. Okay, permutations when order matters, combinations when order doesn't matter, talks about an ordering of things. So it's going to descend down. Notice the factorial descends down. If we talk about a repetition is allowed, that means we have to use this fundamental counting principle. So what we look at is we have 4 separate events that we are selecting. Okay, we are choosing 1 letter. Now, how many letters are in the alphabet? Who answered that out there? There are 24 letters, right? No, there are 26. Okay, so we have 26 letters in the alphabet. And then we have to select a number here. So how many numbers are there to be selected here? So I want you to think really hard. How many numbers do we have, once again, in a 1-unit selection? Okay, so a 1-unit selection here. We have 10 numbers that we can fit into one spot. Yes, 10 numbers. Do you think about this? We have 1, 2, 3, 4, 5, 6, 7, 8, 9, and then the 0 for that 10th one. Okay, so don't forget about that, because we could also have a 0 in here. We could have a 10 here or 10 here. Once again, taking 10 numbers, 10 numbers, 10 numbers, and then 1 letter out of our alphabet, which is 26. So when we multiply all these together, we see that we have 26,000 different codes. Okay, so that means if we had a combination safe or a entry lock where there was a 1 letter and then 3 here, you would have 26,000 different codes that were possible in this spot here. So very hard to kind of get into. Next, we're going to kind of go through some of your calculator operations on how you could work through things. So number 14 talks about 12 factorial. Okay, so if we consider 13 factorial. For those of you who have your textbook and are following along, it was a 13, not 12. So 13 factorial. One way to work at this, we could write it out. 13 times 12 times 11 times 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. And because that's what that factorials mean. And then we could write it out. Or if we have our trusty calculators, once again I like the Casio FX 115, I have the ES Plus, there are different versions of this 115. We could type in 13, and then if you hit shift and then this F to the -1 power, notice then we have a factorial button right there. Brings an exclamation point. And then we can hit equals and notice this nice number that we have. So if I write this number down, it is 622,702,0800. So coming back, putting our commas in, we can see we have 6,227,020,800 is what this value would be. Number 18. 18 discuss kind of working with some of these factorials. Okay, so in this case we talk about 10 factorial over 7 factorial, 3 factorial. Okay, so if we have these factorials written out, once again, we could write out everything that's happening with this. Okay, I can go like this, and I can go 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1 over 7 times 6 times 5 times 4 times 3 times 2 times 1 times 3 times 2 times 1. I can come here and I can say, oh, I got a 7 and a 7, a 6, 6, 5, 5, 4, 4, 3, 3, 2, 2, 1, 1. If you notice, this was 7 factorial right here. So that 7 factorial would have canceled off, and then we would have 10 times 9 times 8, and then had this right, the 3 times 2 times 1. Well, I can cancel a 3 off. I can cancel a 2 off. So if you notice, I have 10 times 3 times 4, which is 120. The other way is we could have typed this into our calculator with those factorials and worked that way with it and been fine. Moving on, let's work a couple different permutation combination ones, some of the basics, then we'll get into a couple more story problems. So if we look at number 22. Okay, so on number 22 here, it tells us 8 permutation 2. Okay, so what this is stating is that we have 8 factorial over 8 minus 2 factorial. Oh, okay, I was going to start writing the combination one, but it's permutation. So we have 8 factorial over 6 factorial. So this is 8 times 7 times 6, 5, 4, 3, 2, 1. 6 times 5 times, so I'm just going to kind of write my factorial here so I can cancel this off. So we see we get 56. Now, on your calculators, okay, kind of bringing it in, you'll see that on this multiplication symbol right here, there's an NPR. Now, some of you have different versions. You could have maybe up in here a PRB button. I've seen that on other calculators. If you click that, you'll see that you'll have this in here. Now, there are some special ways to type this in, once again, depending upon the calculator. You'll want to type in the first number, then you'll want to bring in that permutation, and then type in that second number, and then hit equals, and you see we get our 56. Okay, so on homework wise, I expect to see that we set this up, and then if you're going to use your calculator, you can go straight to that answer. Once again, technology is great. We're using it every day right now, even more in depth than we want to. But that's kind of what we're doing with everything, so I'm perfectly fine if you want to go from this right to this. Just make sure to write this down, that this is what you're using. That way I can tell if you're using permutations or combinations when we get to story problems. If we look at number 34 then, 34, 7 combination 3. So on this one we're looking at 7 factorial over 7 minus 3 factorial, 3 factorial. Okay, so once again, the combinations also takes out an additional factorial of that last one for any repetition as we go through. So if we look at this, this would be 7 times 6 times 5 times 4 factorial over 7 minus 3 is 4 factorial, and then we have 3 times 2 times 1. Okay, so what I did was I used my larger factorial to eliminate out, so I didn't have to continually write out so many multiplications in here. So that would cancel off. We would see that 3 times 2 times is 6, so this would cancel with this 6. So we see that we have 35. Once again, on your calculators, we are doing 7. The combination on this one is the second or the shift of the division symbol right here. And then we go 3, and we hit equals, and we get 35. So once again, a very easy way to go to that answer. Just kind of trying to tie in the fact that we want to make sure that we're using the correct responses for what's happening, and not overthinking the problem, but not underthinking the problem. So let's start looking at some word problems, okay? Because this is going to be one of the hardest things to do in this section, is trying to distinguish what is going on. So number 38, there are 8 swimmers in a competition where the top 3 swimmers advance. So we have 8 swimmers, and then top 3 move to the next swim meet, or move to the next event. So kind of like the Olympic trials, even within the Olympics, they have so many that go off, then they take the top 3 to the next round. And then they run another round and take the top ones until they limit down to having your final race. And then in that final race, you have it going. So this doesn't matter if you finish first, second, or third, you're moving to the next round. So order does not matter. So we have a combination. Okay? We have a total of 8 swimmers that are possible. So that's my n, that's my total number, is 8 swimmers. We're looking at taking 3 positions. So we're taking the top 3. So that's kind of how that N and R work. The first one is our total positions. The second one is the number we're starting to look at towards and how many we want within. So if we do our 8 combination, so 8 combination 3, we see that we get 56. Okay? So on a homework problem, this is what I probably would see from you. I would see this part right here, knowing that you are considering a combination, and then what that answer would be on this. Number 40. Okay, so on number 40, it says, for each situation, determine whether to use a permutation or a combination, and then solve the problem. So it says, suppose you find 7 equally useful articles related to a topic of your research paper. In how many ways can you choose 5 articles? Okay, so we have 7 equal articles, and we're going to choose 5 to use. Okay, so considering what's happening here, looking at the problem, are we going to have to use a permutation or combination? Is the order going to matter which article we read? Well, if we register the words 7 equal articles, that means they're the same. We don't have to do one and then the other and then the other. There's no order within. There's no necessary means for this. It doesn't matter how we're choosing our 5 because they're all the same information. Okay? So because they're equal articles, here we would look at having 7, and we're going to choose 5. So if we take 7, combination 5, we see then that we get 21 ways. Okay, so we have 21 different ways that we can go through and figure out which articles we would want to choose. Once again, that's choosing 5 out of 7. Number 50. Number 50 talks about a consumer magazine. Okay, so a consumer magazine relates televisions by identifying 2 levels of prices. Okay, so we have 2 levels of price. Then we have 5 levels of repair frequency. So 5 levels repair frequency. Then we have 3 levels of features, so 3 levels of features, and then 2 levels of picture quality, so 2 of picture quality. Kind of ran out of room here. It asks us how many different rankings are possible. So if we consider we're not choosing an amount out of so many, okay? You know, that's when we talk about permutations, combinations. We're choosing so many out of a total, okay? We have so many within. It's basically one event that's going on. We're just choosing multiple ones in this one event. We have completely separate things going on. So we're going to have to use our fundamental counting principle, and we're going to have to look at our options in price, repair, features, and quality. So I'm just going to go price, repair, features, and quality that we have here. So we have 2 levels here, we had 5 levels here, we had 3, and then we have 2. And then we're going to look to multiply each of these together. Okay? So if we multiply each of these together, we see 2 times 5 is 10, 3 times 2 is 6, so 6 times 10 is 60, once again, levels that we're in relationship to here and solving towards. So once again, please remember that you have to pay attention to whether we have a fundamental counting principle. Let's bring the sheet back in here. Whether it's going to be the fundamental counting principle, permutations, combinations. One of the things that I can tell you here is do realize that if we are within one event, we're choosing so many within something, and so we're only doing one thing, that's when these permutations, combinations come in. But if we got different categories, different things going on, we have the fundamental counting principle. Now as we advance and we keep moving, there are times that in this fundamental counting principle here, this would be a permutation, this would be a permutation, this could be a permutation, and we could have stuff within there. So don't discourage and say, oh, well, it's different events, I can't use a permutation. No, you can probably use it to figure out the number that could go here, the number that could go here. So do be well aware that as we advance on and keep moving further, things do get to be a little bit more complicated.